Hello. So I forgot to share my desktop. Go. Week 3 is at its end here. So here's a little overview of the week. So we're doing summary statistics. An example, here in StatKey, I have the body temperatures of 50 random individuals. And you can see the dot plot. Each of these dots is a particular person that was sampled. Viewed as a histogram, we can see the average is somewhere over here. Median's probably about the same place. We have a mean of 98.26 and a median of 98.2. Box plot. Okay. Got one outlier out here, probably has an illness, given that high temperature. Summary statistics. Sample size is also important. Mean, standard deviation, those two go together. And then the 5-number summary, minimum, quartile 1, median, quartile 3, and maximum. Remember, quartile 1 is a position in the list. So this says 97.8. So somewhere over here is that first quartile. That represents the point where there's 1/4 of the data at or below that point. So there's a quarter of the data. That's a whole group of measurements. And then there's a quartile, which is an individual measurement marking the cutoff between the first quarter and the second quarter. And so quarter is a region, quartile is a position, for an idea. Some other important ideas. Median and mean are a measure of center of the data. Mode isn't exactly a measure of center, but it's put in the same category often. It's more useful for categorical data, not quantitative data, like eye color, like gender. Here are median is just a hair below, right about there is our median, all that. And this outlier over here kind of pulls that mean away from the median. Median is not affected by outliers, so it wouldn't matter whether this highest number was 101, 103, 100, or 99.9. Any maximum in this region right here is going to affect the mean, but not the median, because the median is just the middle number. It doesn't matter how far the min and the max are from that. But it does matter for the mean because of the way it's calculated. So, another big idea. In statistics, we take samples to try and predict what's going on with the population. So we call the population mean mu. That's this Greek symbol right here. It looks kind of a cross between an M and a U, and it's the Greek mu. That's the population. We always desire to know what's the average for the population. But the best we can ever do is make different samples. So I have one sample over here that says the average body temperature is 98.26. Now we usually say it's 98.6, so what's going on here? Well, maybe I need to do more samples. So there's lots of ways to do that, and we have great sampling techniques we went over in Chapter 1. So we'll take a look at that some more in a minute. Standard deviation is the average spread of a population or a sample. In the population, we use the Greek letter sigma. That's what we're looking for to try and calculate what's the average spread in the population. The best we can do at any point in time is come up with a sample, and we use the sample as an estimate. So this is a big idea. We use summary statistics to try and abbreviate data, but we also use it to try and predict population. Okay, so important. Samples and summary statistics are used to predict population values. So pretty soon we're going to start getting into what's called inferential statistics. So given some sample, we're going to try and predict things about the population. And these values for the population are called parameters. So the mean of a population is a characteristic of it. It's called a parameter. The mean of a sample is a statistic. Okay, so we have sample statistics, we have population parameters. Now, I can also use software to do repeated samples. So I want to take a look at that here. So here's one sample of 50 individuals. StatKey has another section about inferential statistics. I'm using a section called confidence intervals for means. We'll take a look at that in about 1, 2, 3 weeks from now. And here's my original sample dot plot. And what I can do is ask the computer to use a special program to shuffle the data. And if you want to know more about the shuffling technique, send me a note and I can explain a little bit of it. So here's a reshuffled version of these numbers right here. And it's kind of like, this is maybe cards from a huge deck. And then I throw all those cards back in the deck and I pull some 50 cards out again. I'm going to get a slightly different group each time I do that, right? So this is a different sample. And the mean of that particular sample is 98.12, and it's represented by this dot right here. So I can ask StatKey to generate another sample. And so I have a different box plot right here. It's different than the previous one. That's this one over here. So I can switch back and forth between them. And this one has a mean of 98.4. And I keep asking StatKey to please reshuffle the data and give me a new sample of 50. And so here's another one somewhere over here. And so every time I get a new dot on this screen, that's the average of a sample, and I can take a look at what that sample looks like. So I could do these one at a time all day. I now have 10 different samples based on the original 50 people body temperature I had. And each of those new samples has a different mean and a different, slightly different distribution, different histogram. So here are all of them. In statistics, we can call the mean a sampling variable, right? Because every sample is a little bit different, and so that means it's going to have a different mean. That means the mean varies from sample to sample. So the mean is a sampling variable. Kind of make sense, the way I'm using that phrase? So I could generate more. I could grab 100 different samples, and every one of these dots is the average from a new shuffle over here of the original data. And so they're all going to have slightly different histograms when I point to their dots here. Okay? And they're shown here, right? And here's always shows the original right there. So I could do another 100 and another 100. I could even say, hey, give me 1,000 of them. When you do repeated samples and look at the means, and you make a histogram of the means of the samples, that's called a sampling distribution. So let's put that in the notes here. So a statistic, like the mean, can be considered a sampling variable. Every sample will have a different mean, therefore the mean's variable. So it's a sampling variable, okay? Because they change. When you look at a whole bunch of different samples and you make a histogram out of their means, you get what's called a sampling distribution. And this is a super powerful idea that we're going to take a look at in weeks 6 and beyond. So chapter 2 introduces the idea of a sampling variable, which could be the mean, could be the median, could be the mode, could be the standard deviation, could be the count, right? There's lots of different sampling variables. It's anything that can vary in a given sample. And then when we sample over and over again and make a histogram based on a particular variable of that sample, like the mean of each sample, we get what's called a sampling distribution. And a distribution is just a picture of how the data is spread out. But instead of looking at individual people, each of the dots in this plot right here is the average of a particular sample. Notice the shape of it. Okay? It's rather symmetric, might have a little bit of skew one way or the other, and sometimes identifying skew is very difficult depending on the histogram. Sometimes it's easy. There are technical ways to calculate skew. We're not going to worry about that in this class. So just some ideas I wanted to plant now that'll help us when we move on to some other stuff in the near future. Another idea, which wasn't in the book, but I talk about it I've got a final assignment for this week that's kind of like a pop quiz about the average student. So I took the average student data over here, average person, and this particular chart is just the Math 243 students. And notice I have calculated the averages for each column where it's applicable. This number right here means it's almost 85% females in this class, which is not unusual. So here, average height of a student is 67.3, average weekly income is almost $350, average sleep is about 7.1 hours. And although some people said they get 8 hours and 7 hours, some people said 5.5, 7.5. And if we did actually record the hours of sleep we get, it wouldn't be a whole number. So it makes sense to say the average could be something like 7.1. So sometimes having decimals in a statistics makes total sense, but sometimes it doesn't. So for example, at the end, I asked how many motor vehicles people own, and here it says 1.5 motor vehicles. Well, if you have half of a motor vehicle, it probably doesn't run. So I don't think that counts. So what does it mean to have 1.5 motor vehicles on average? So here is an instance where I have a statistic that couldn't actually be a number in the data set, which is a bit of a problem. So in this case, we have to interpret that number to say, well, although the average is 1.5 motor vehicles, that I would have to say that means on average people have 1 or 2 motor vehicles on average in this class. How many animals do you own? You can't own 7/10 of an animal. That doesn't make sense, right? So what we could say is the average in this case means that on average people in this class have 3 or 4 animals, more likely 4 than 3. So we could round that up there. And so we have to be careful about interpreting these numbers and not just stating them sometimes. Another idea with respect to sampling statistics is the idea of the coefficient of variation. So an example, I got 3 examples of the coefficient of variation, but I'm going to use a slightly different one. So I'm 1 inch taller than a friend of mine. Okay? So if I was 6 feet tall, being 1 inch taller isn't a big deal. On the other hand, we have little kids. Our kids are about 3 feet tall. Now, being 1 inch taller, if you're 3 feet tall, is a big deal, right? So let's look at that quickly for a second. What is 1 out of 60? And I get 0.016. So I'm like 1.5% taller than my friend. But if I look at 1 out of 36 inches, that is now almost 3% taller, okay? So a change in some amount, a change of 1 can matter whether that original number was small or whether that original number is big. And the coefficient of variation kind of takes that and applies it to the relationship between spread as standard deviation and middle as mean. So if you take the standard deviation, let's write this down, STD, and you divide it by the mean, and you turn that into a percentage, so you could then multiply that by 100%, that's what we call coefficient of variation. So for example, if we look at the amount of sleep, and here I am comparing, these are algebra students, so math 70 students, and these in green are math 243 students, so stat students. So on average, stat students get more sleep, and there's more spread. Okay? Now, you can't just compare their standard deviations, their spread, because it depends on where the middle is. So here, the spread, the coefficient of variation tells us that the spread is 16% of the center, 6.2, and for stat students, the spread of 1.5 is 20% of the mean, 7.3. Okay? So they do have different percentages, so that when I'm comparing two populations, I can't directly compare their standard deviations if they have different means. If they have the same mean, no big deal, we can compare the standard deviations. But the coefficient of variation gives us a way to compare STDs, standard deviations, of different samples. And it's a powerful summary statistic that's sometimes used because we often compare different samples or different populations, males versus females, algebra students versus statistics students, Democrats versus Republicans, all kinds of different things like that. All right, so again, some hidden highlights of the course. Get my thing to work, there you go. That we're playing with summary statistics. Two powerful ones are the mean and the median, and they are representations of center of the data. They tell us slightly different things. A point of having summary statistics is not just to create a summary of a big set of numbers, because that's useful for us humans. Big set of numbers isn't very useful, but it's also a way to kind of predict what's going on with the population. Repeated sampling is important because then we can create what's called a sampling distribution, and that gives us more power in predicting things about a population. And that's something we're going to dive into in the second half of the course. That idea is introduced in chapter 2, which we're on now. A summary statistics that wasn't presented in the book is an idea of coefficient of variation, which is the standard deviation as a percentage of the mean. Just divide the two, multiply by 100% to get it as a percentage. And that just gives us a way to compare the spreads of two different data sets because they probably won't have the same mean. Okay? So I hope things are going okay this week for you and you're tying up all your assignments. Again, there's that kind of surprise quiz I added here at the end of the week, which is the average statistics student. So take a look at the data from that survey you took earlier. You have a couple of different things you could tell me about, either the average statistics student or the average online community college math student are the two things you could tell me based on that data set, and use everything you've learned in chapters 1 and 2. Have fun, do good math. I'll see you in the future.